Hello everyone. Today we will discuss about the application of Huygens principle to understand the process of refraction, right? So here we are actually proving the laws of refraction using Huygens principle. So for that we need to take two cases. One is when the ray is moving from rarer to denser medium. So let's consider an interface. This is the denser one. And a wavefront. The incident wavefront is this one. If this is the incident wavefront, the ray is always perpendicular to the wavefront. So we can draw the rays like this. So this is the suppose this is our wavefront, incident wavefront. So this is the incident wavefront. We know that the ray is normal to the wavefront. So if this is the incident wavefront, how will I draw the ray? By drawing a perpendicular. So at this, if this is the point of incidence, so we can draw this 90-degree angle to show that this is the incident ray, because incident ray is perpendicular to the incident wavefront. Similarly, we have one more incident ray which is also obviously perpendicular to the incident wavefront, right? So this is perpendicular. Now we have to draw the normal on the surface. If this is the normal, and here then the refracted ray will bend towards the normal because it is moving from rarer to denser medium. So this is the refracted ray, right? Now here this ray would also have gone refraction. This has taken more time to reach here. Now here the refracted wavefront will be perpendicular to the refracted ray. So this one is the refracted wavefront. Now this is incident ray. This is also incident ray. This is refracted ray, right? And what will be the angle of incidence? The angle of incidence will be this. this will be angle of refraction, and angle between two lines is equal to angle between their perpendiculars. So if we look at this line, its perpendicular is this, and if we look at this line, its perpendicular is this incident wavefront. So angle between these two is equal to angle between these two. So this angle will also be angle I. Similarly, this is normal, this is the base. So these are perpendicular. This is the refracted ray and this is the refracted wavefront. So angle between the refracted ray and normal will be same as angle between this refracted wavefront and the base. So this will be actually angle R, right? Now the same time will be taken by a point over here to reach here and the point over here to reach over here, because these were the points on the same incident wavefront. So these will reach the same refracted wavefront. So if v1 is the speed of light in this medium, then v1 into t, right? This is the distance traveled from this to this point. Similarly, here the time is same, so this velocity multiplied by time, this will be the distance traveled in this medium. Now we can find, we will first mark the points A, B, C, D, right? So in triangle A, B, C, sine I is perpendicular upon hypotenuse. Perpendicular is what? This BC. Upon hypotenuse is AC. BC is what? V1T and AC is AC, right? Similarly, we know that this angle is 90-degree refracted ray and refracted wavefront. So in triangle ACD, sine R is equal to again perpendicular upon hypotenuse. So perpendicular is V2T upon AC, right? So we can find the ratio sine I upon sine R. If this is 1, this is 2. So 1 divided by 2 gives sine I upon sine R is equal to V1T upon AC upon V2T upon AC. So this gives me V1 upon V2. Now let's find out a relation between refractive index. If this is our medium 2, this is medium 1, this is denser, this is rarer. So we can write the refractive index of medium 1 with respect to air, refractive index of medium 2 with respect to air. This will give speed of light in air upon speed of light in this medium. Similarly, this can also be written speed of light in air upon speed of light in this medium. We can mark this as 3 and this as 4, right? We have to find, if we divide 4 by 3, what will we get? A and 2 upon A and 1. This is equal to C upon V2 upon C upon V1. This gives us V1 upon V2. And this is actually and 2 with respect to 1. And this is equal to V1 upon V2. If we mark this as equation 5 and this as equation 6. From 5 and 6, sine I upon sine R is equal to 1 and 2, and this is Snell's law. So you can say that here this first law of refraction is proved. For the second law, we know that incident ray is perpendicular to incident wavefront, refracted ray is perpendicular to refracted wavefront, and normal is perpendicular to the refracting interface. So that means all these incident ray, refracted ray and normal lie in the same plane. Therefore, second law of refraction is proved, which says incident ray, refracted ray and normal lie in the same plane, right? So this was all about the verification of the laws of refraction when a wavefront is moving from rarer to denser medium. We can prove this for denser to rarer medium case also. Everything will remain the same except the diagram, right? So first I'll have to rub this and then we can move on. So the written part will remain the same and rest of the things I am rubbing and I am drawing a fresh diagram for the second case. So when a wavefront moves from denser to rarer medium, the diagram will be different, and in the exam sometimes it is mentioned specially that you have to discuss it for denser to rarer or rarer to denser. So in that case, if the diagram is not up to the mark, the marks are not given. So first, the interface. This is the refracting interface. Now this is the denser medium. And the second one is the rarer medium. Now our light ray is passing from denser to rarer. That means our wave front, incident wave front is this one. So the incident ray will be perpendicular to this incident wave front, and here also I am taking another incident ray which is also perpendicular to this incident wave front. And normal, this is the normal. Now when this ray moves from denser to rarer medium, where will it move? It will move away from the normal. So it is now moving away from the normal. Now this refracted wave front will be perpendicular to the refracted ray. So this is our incident wave front, and this is our refracted wave front. This is normal to the refracted ray. This is incident ray, and here this is the angle of incidence. This is the angle of refraction. Angle between two lines is equal to angle between their perpendiculars. Like before, if this is the incident ray, this is the incident wave front. So these incident ray and incident and normal. So angle between these two will be equal to the angle between their perpendiculars. For incident ray, incident wave front is the perpendicular. For this normal, this base is the perpendicular. So you can again say that this is angle of incidence. Again, if this is the perpendicular, or you can say the normal, so this is the base, this is the refracted ray, so refracted wave front is perpendicular to this. Angle between these two is equal to angle between their perpendicular, so this makes it R. Let's mark those points same as the previous figure, so that we can use the same written material in that case. A, B, C and D, right? And V1 is the speed in this medium. This is our medium 1, which is denser. This is our medium 2, which is rarer, right? And in this medium 2, V2 is the speed of the light. So rest all is same. So this way only the diagram will be different for this case. Rest of the things will remain the same. So that's all about application of Huygens principle for proving the laws of refraction. That's all for now. Have a nice day.